So as we saw in the above example, if we wanted to find the probability of A and B occurring, that would be this rule here, rule 1. The probability of A and B is the same as taking the probability of A and multiplying it by the probability of B given that A actually occurred. The way we can write that is we say that we're multiplying the probability of A, the first event, multiplied by the probability of B, but this B has to be the event such that it's given that event A has actually occurred. So we write our formula like that. Okay? It's very similar to what we saw on the previous page. Keep in mind that conditional probability is saying the probability of event B given that event A actually occurred. And you can see here that that probability, 48 over 51 or 3 over 51, that can change depending on what happened in event A. Now, as I take a look at this formula, what I do notice is, if I were to rearrange a couple of things, okay, so first of all, if I had probability of A and B equals probability of A times probability of B given A, then if I wanted to solve for probability of B given A, I could divide both sides by probability of A. And that's exactly what probability of B given A is actually equal to. It's equal to the probability of A and B divided by the probability of A. Okay. Now, it turns out that, sometimes this B given A, you may get a number that shows you that you have conditional probability, or maybe you don't have conditional probability. And in that case, you would actually have where events A and B are independent of each other. That probability of A and B, it may even equal the probability of A multiplied by the probability of just event B. If you find that these two things are equal, then that's showing you that A is not being affected by B. Okay, so if this happens, I'm just going to write down it meaning that A does not affect B. Okay, so if you find that these two statements right here are actually equal to each other, then this is telling you that you have independent events. Okay, so they are independent events if they're equal. Okay. Let's take a look at an example where we actually discuss whether something is independent or not. Example 4. 2 dice are rolled. Event A, where both numbers are the same, and event B, where the sum is 6. Show that these are not independent events. All right, so now that we're dealing with 2 dice, we're actually going to have to come up with a unique and different way of showing all the possible outcomes. Unlike the example we saw up above where we did a tree diagram, I don't think a tree diagram would make very much sense if we're rolling 2 dice, just because you have 6 total outcomes for each dice, and that would just get really, really confusing with all those branches. So instead is we're going to make a table. We're going to say that die 1 has the possible outcomes of getting a 1, 2, 3, 4, 5, 6. And dice 2 also has the possible outcomes of 1, 2, 3, 4, 5, 6. So in this way, I'm just going to go ahead and show what my possibilities are. For example, if I roll a 1 and a 1 for dice 1 and dice 2, I can represent that by like saying 1, 1. If I rolled a 2 and then a 1, or rather a 1 and then a 2, I could say, oh, I have a 1 first, and then I rolled a 2 on my second dice. And then here I roll a 1 first, and then a 3 on the second dice. And so on, right? So I can keep doing this. And then maybe now I roll a 2 on my first dice, and then I roll a 1 on the second dice. And so as you can see, we can build a table that represents our values. It's almost like looking at ordered pairs, I would say, on a coordinate plane, and just kind of giving all the possibilities that could exist if you roll the die. So I'm just going to go ahead and write those values in now. There we go. Okay, so with all those possibilities, let's actually figure out what are the events. First of all, the probability of event A, where what it's asking for is the probability that the numbers are the same. So if we take a look at our diagram, as you can see, we have a 6 by 6 grid, so we know that there's 36 possibilities. But where are the numbers the same? The numbers are the same if you ever get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, those numbers there, right? So how many numbers are there? It looks like we have a total of 6 possibilities out of 36, so we have a 1 in 6 chance there. Okay. Let's take a look at another scenario. Let's look at probability of event B, where the sum, the probability that the sum is 6. When do we get a sum of 6? Well, they have to add up to 6 then, so maybe a number like 1 and 5, and so on. So 2 and 4. Look at that. We also see that it is formed by a diagonal, getting us a sum of 6. Okay, so how many do we have there? 1, 2, 3, 4, 5. So we have a 5 in 36 chance of getting a sum of 6. Show that these events are not independent. So keep in mind what we're looking for. What we want to show is, does probability of A times the probability of B, does it actually equal the probability of event A times the probability of event B, given that A actually occurred? What we want to prove is that it's not equal to. So let's go ahead and do that. On the left side is quite simple, because all we're taking here is the values we found, which was, let me do this in the same color actually. So we have the 1 in 6 chance the probability of A times the probability of B, which is 5 over 36. And we want to see if that's equal to the probability of event A. Now that doesn't change. That's still going to be a 1 in 6 chance. But now we also need to find the probability of event B given that A actually occurred. We're going to have to actually do something different there. So given that A occurred, A has to occur, meaning the numbers are the same, which are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Given that A occurred, we then need to find the probability of event B. Event B says that we have to have a sum of 6. When do we get a sum of 6? Well, 1 plus 1 give us 2. That's not it. 2 plus 2 give us 4. That's not it. 3 plus 3, that's the one. We want a sum of 6. Nothing else will give us a sum of 6. So the probability of event B getting a sum of 6, given that you actually have the numbers being the same, is a total of a, here in this case we see a 1 out of, how many total do we have there? 6 chance of getting that probability. Okay, so if we just do the math here, we just go ahead and multiply 5 over 216. Is that equal to, well, we can definitely see this is not equal to 1 over 36. And therefore, these are not independent events. Keep in mind that in order to prove independent events, this is the big formula you want to be showing. That probability of A times probability of B equals probability of A times probability of B given A.